And hello, welcome to this video. In this video, I'm just going to discuss some methods that were used to solve Blasius Equation. Yeah, this equation isn't exactly very trivial to solve by hand, and you probably need some sort of software to do it numerically using the Runge cutter method. And after that, remember why we want to calculate this flat plate thing is to actually get our wall shear stress. Okay, wall shear stress. So I'll not be going through derivations and how to solve it in this video. I'll just go through discussions of what was actually being done. Okay, so in Blasius's original paper, he actually used something known as a series solution. Okay, series solution to solve for f. Okay, he didn't use f in this equation, but it's basically f. Okay, he used a series solution. So let's see, paragraph, series solution, aka Frobenius method. Some people will say Frobenius method, and if you're not sure what it is, it's just you basically get a series solution. So I'll just paste the Wolfram thing here, verbatim. Okay, and this is what he actually used in his original paper, because there are no computers back then. You have to calculate everything by hand. So the series solution basically assumes f equals to some sum of let's see, eta equals to 0 going to infinity. Okay, so if I'm not wrong, it's eta. Yeah, this is eta. Okay, so you have some constants here, and eta to the power of what? Yeah, never mind. Eta to the power of n. Okay, so you don't go by this I equals 0. You use n. Okay. So you substitute. Okay. Basically, you substitute this expression in. Of course, you can do your derivatives, which in Wolfram here you'll see. I'll just do very shortly for you. I'll just copy and I'm literally copying things down. Okay, so it starts from n equals to 0, n plus 1 here, n plus 1 into n plus 1. Okay, so if you differentiate all of this, that's what you'll get. F prime, and you have f double prime, f triple prime, so on and so forth. Okay, you don't really need to go all the way up. So double prime will be plus 2 over here, am plus 2. Alright, so m plus 2, yeah. Okay, so this is the double prime. If you go in the triple prime, you differentiate this whole thing again, you'll do the same thing. The triple prime will be as such. If you can start seeing the pattern here, m plus 3. Okay, I'm not going to solve it, but basically, what you do is that you substitute these expressions in. Okay, you differentiate these slowly. You substitute all of these back in here, and you solve. That is what the Frobenius method is about. Okay. The other method is Runge cutter, and you probably need an Excel, at least an Excel or something. Runge cutter methods. So these are family of methods. Let me close this up. Close this, close this. Yeah, this is the Runge-Kutta method. Online you will be able to see some what do you call that? Yeah, Blasius solution Runge-Kutta. Okay, so even MATLAB has it. Okay, so this is a very classic thing. Oh, okay, it's not. Never mind. Yeah, you can just search online Runge-Kutta methods. This will give you the Blasius solution. Of course, sometimes you will see in front of this in some equations, sometimes there will be a factor of 2 on one of this. It really depends on how you define eta and f. But at the end of the day, when you want to calculate wall shear stress, you want to calculate velocity profile, none of this really makes too much of a difference. So let me just paste it. So Runge-Kutta is basically just numerical methods. All right. Okay. And what you'll probably do, you have to develop some sort of algorithm to get this done correctly. And I'm not going through this in this video, but this is just an overview of how this Blasius solution is actually solved. If you want to take a look at what the actual Blasius solution looks like, not this. Okay, so I mean there are lots of PDFs online you can look for. I'll just say you can cite this paper. You can download the full text in PDF here, no problem. But yeah, I'll not go through how to solve it through the Runge-Kutta method. Suffice to say, this is basically just classical numerical methods, okay, of solving this. We discretize this, and then we take small steps in eta, and we kind of iteratively progress until we find it. Now I'm going to talk about the algorithms or what here in this video. But this is just to help you understand how to solve this. And if you really wanted the table, I mean how f and eta actually what do you call that, vary, you can look at some of these what do you call that, documents online. This one's from the ResearchGate one, is one of such documents. Of course, they solve a slightly different ordinary differential equation. There's a factor of 2 in this equation here for one of the terms, but again, that's more or less how they do it, using numerical solutions. But yeah, if you want to take a look at doing it by hand, then I'll suggest this Frobenius method. Okay, series solutions, and then you kind of iterate up to maybe the 5th term or 6th term. Okay, then you kind of just truncate it. That's a quite approximate solution for Blasius, and this was how it was done in the early days. Okay, so that's all I have. Just discussing some solution methods for a Blasius equation, and I'll probably move on to some other topics. Yeah, if no promises about actually getting Runge-Kutta methods done. If I do it, I'll do it. All right. Okay. So thanks for watching. See you again. Bye bye.